Hello everyone. Today's topic it is relocation loader. Before we start with the relocation loader, I request you all to go through this video which give you the introduction to the loader that can have the functionalities of the loader, and also very importantly which also describes about the functionalities and the working of the absolute loader. So before we start with today's topic, which is on the relocation loader, I want you guys to be thorough on this absolute loader. So only before we start with our current topic, please go through this video which will give you a complete overview of the absolute loader. Okay, now let us start with our topic, relocation loader. As soon as you say the term relocation, however you understand this, it is not reallocation, it is relocation. At the time of loading, there may be the possibility of relocating the object code. Instead of you store at a particular location whatever it is given by the assembler, the loader may relocate to the different address, different position, different location that will be carried out by the loader, so which is a relocation loader. So as a means of a relocation loader which varies from the absolute loader will store the object code into the same location which is specified by the assembler into the main memory, whereas a relocation loader which will not or which may not load to the same location which is specified by the assembler, it may relocate the position, it may relocate in the main memory, which is just a basic concept of relocation loader. Now let us see in detail. So here are the three major points when you cannot make use of the absolute loader, or in the other way, if you make use of absolute loader, these are the three main issues which will come across. What is the first one? It is that actual address. So you can see the actual address may not be available in the main memory. What I mean to say, see, this is what an example. Consider this is the source program or the object program generated by the assembler, wherein it has considered the 0 as the starting address and 1070 as the last address. But when you are trying to load into the main memory, this is what in my depiction, this is the main memory depiction. So when my main memory, in this main memory, so I supposed to load this program, I supposed to load this, or a loader is supposed to load this object program into the main memory starting from the 0. But the problem is, what if the main memory is not available from the 0? What if the main memory is not available from the 0? It may be available from somewhere else like 500. So if the main memory is not available free from 0 to 500, so if you make use of absolute loader, you are supposed to load this object program at the starting from the 0 itself, because you can't load anywhere. That is what I mean to say. It cannot relocate to some other position. It has to be located at the same position when you make use of the absolute loader. So that is the first point, says when the main memory is not available at the preferred location, so then in such case you cannot make use of the absolute loader. So wherein this is the depiction, that this is the object program wherein started from the 0 and the last address it is somewhere like 1070. So it's supposed to be loaded to the main memory. If you make use of absolute loader, it has to be loaded at the starting from the 0 itself. But what if the main memory is not available free from the 0 to 500? If it is not available from the 0 to the 500 memory space, then you cannot make use of absolute loader to load this object code into the main memory. That's the first point. Coming to the second point, you cannot run the several independent programs which are sharing the same memory. What I mean to say, see, here is an example. Again, I assume these are the three object programs. And I consider this is the memory architecture, or this is the memory space, and there are three object programs. And if you observe clearly, the starting address for all the three object programs, it is specified as 0 itself. Suppose if you want to run all the three at the same time, And can you make use of absolute loader for this? In the sense, no, because if you make use of absolute loader, it's supposed to be stored A at the into the main memory space, which start from the 0 itself. When you stored program A into the main memory starting from 0, so then it cannot load B, because B also in the object program of the B also starting from the 0, and the C is also starting with the 0. So if you make use of absolute loader, you cannot load all the 3 into the main memory, because the starting address for all the 3 programs are same. In such case, so you cannot make use of the absolute loader. And the third one, again, it is with respect to the whenever there are the multiple subroutines, if you are making use in your program, in such case those cannot be loaded into the main memory at the same time, so they cannot be used efficiently. So those are the 3 major drawbacks which will come across with respect to the absolute loader. When you are loading the object program into the main memory, you can't expect the main memory to be available free wherever you are specified with the starting address. So that is where the machine independent loader feature came into the picture, wherein we will be making use of the different kind of loaders instead of the absolute loader. Among the first and foremost, it is the relocation loader. So that is what today's our topic, it is relocation loader. So now, as I already said, for these 2 examples, somewhere like, so per suppose if you are loading this object program, or if you want to load this object program into the main memory, wherein the main memory is not available free from the same address, what can be done in the sense? Obviously you can't make use of absolute loader, or to load to the specified address is 0, it has to be relocated, shifted to some other location, like starting from 500 somewhere. If you start from 500, then the last address will be, instead of 1070, it will be around 1570. So then what about this case? So where you have 3 object programs of the same starting address, so what to be done? So it's supposed to be, so first you need to load A, then you need to load B, then you need to load C. In such case, there may be the possibility that A may not relocate. For the A, the starting address can be 0 and the last address would be 57, wherein after this A you supposed to load the B, and after this B you supposed to load C. So that address of the B and the address of the C will vary. That is by using the relocation loader. That is what the depiction here, if you can observe. So here we have the 3 object programs, wherein all the 3 object programs has the same starting address, which is 000. The length of the 3 object programs may be varying here. The first object program may be from 0 to 57, which requires 57 bytes. In my means, I consider as a bytes. So wherein B, which requires 0 to 13, which requires only 13 bytes, whereas C, which requires 0 to 34 bytes. So the length of the 3 object programs may vary, but the starting address for all the 3 object programs looks same. So in this case, you cannot make use of the absolute loader to load all the 3 at the same location. So there is a necessity of relocation. That is what I mean to say. It is a relocation. It is not reallocation. It is where you are shifting the location. You are changing the location. That is what relocation. But in this example, let us see which will be relocated and which will not be relocated. Per suppose I assume that in the memory space from the 0 itself you can load. If you assume that you can load from the 0 itself, so the object codes belongs to the object program A can be loaded to the main memory starting from the 0 to the 57 itself. So it means to say that there is no need of relocation for the program A. There is no need of relocation for the program A, because it is loading from the 0 to 57 itself. Now, so if you want to load the B, you can't, and the starting address it was 0, and you can't load this B to the main memory starting from 0, because A is already occupied here. So what can you do in the sense, instead of you load at the same location 0, you are going to relocate to the next byte. So B will be started loaded from the 58 onwards. It will be loaded from the 58, and as however we know the length it is 13. So if it start from 58 and the last would be 71, the last address would be 71. Again, as usual, once after the B is loaded, then C is about to load. But if you want to load C, again as usual, the starting address for the C, it wants 0, and you can't load this C to the main memory starting from 0 because A is already occupied here. So C is supposed to be relocated to the some other location, but which location it is after B? Here we are considering that C will be loaded from 72 onwards, and it requires 34 bytes, so it will be from 72 to the 106. So like this, in this example, if you observe, so the program A is not relocated, it is located at the same location from 0 to 57, whereas program B and the C are object programs or object codes belongs to B and the C are relocated to the some other location. That is what I mean to say. It is not reallocation, it is a relocation. You are going to change the location in the main memory space whenever it is not available. So you supposed to be load this B at the 0, but it is whenever it is not available free, you are going to relocate this B to the next available space. In the same way C also, it will be relocated to the next available space. That is a simple concept of relocation, for which you will be using the loader which you call as relocation loader or relocatable loader. But here is the point, here is the question that, so from that time I am using the sentence that relocation loader or relocatable loader will load to the main memory from where the main memory is available free. But who will give you that free space, or who will notify to that relocation loader such that from where the main memory is available free or not? For that, it is that operating system. Now you can see here, this is the complete flow you can observe. So as usual, the source program will be given to the assembler will generate the object program, and that object program, once it is given to the relocation loader, now it is the functionality of relocation loader. Relocation loader has to load to the main memory, load this object program into the main memory wherever the memory is available free. But from where it will fetch? From the operating system. So that is what you observe. Relocation loader, as soon as it gets the object program, your relocation loader will fetch the starting address from where the main memory is available free. It will fetch the starting address in the main memory from where the main memory is free. From where? From the operating system. So operating system will give you that link. Operating system will give you the starting address from where the main memory is available free. So from there your relocation loader will start loading. So that is what, so the three major functionalities of the relocation loader I just described here as, it will read the object program. So because the input to the relocation loader is the object program itself, so it will read the object program, then it has to start loading. But before start loading, it has to know the starting address from where the loading has to start or begin. But who will give the starting address? It is the operating system. So your operating system will give you the starting address from where the loading can begin. Once after it gets the starting address, then it will start loading the object codes into the main memory continuously. But those object codes may be the actual object codes, or it may be a updated object codes. What I mean to say actual updated in the sense, remember whenever the relocation occurs, so whenever the relocation occurs, address of each and every instruction will vary. In turn, the target address in the object codes will vary. If the target address in the object codes will vary, then it means to say that you need to update that object code and load it to the main memory. If the target address doesn't vary, then you will be loading the actual object code itself into the main memory. So that kind of updation will also be taken care by the relocation loader itself. So in that perspective, so moving to the next. So let's see, today we will be dealing with how the relocation will be handled with respect to SIC mission and also SIC mission. So we'll be dealing with both the architectures, SIC architecture and SIC architecture. Remember, for dealing for achieving the relocation in SIC architecture, we will be using the relocation bit. Whereas in case of SIC architecture, we'll be making use of the modification record. So those are the two ways of dealing with the relocation in SIC architecture and XC architecture. So in SIC it is the relocation bits, and in SIC XC it is the modification records. So before we see about how those can be, you make use of those modification records and relocation bids. First let us see the necessity of the relocation in case of SICXC. First, starting, if you take up in case of SICXC, I hope you know that in a SICXC instruction, out of the, other than the assembler directive instruction, all other instructions are categorized as, will be put in the form of any of the four formats, format 1, 2, 3 and the 4, wherein in case of format 1, you will never make use of address. So in case of both format 1 and format 2, you will never make use of any address. When you don't make use of address field to generate the object code, for format 1 and format 2, as you do not make use of any address field, what if the relocation occurs or not? So object code belongs to the format 1 and format 2 will never vary. So it means to say that whenever the relocation occurs, format 1 instruction and format 2 instruction will not be affected. Our object codes belongs to the format 1 and format 2 will not be affected. What about format 3? In case of format 3, we do make use of address in the form of displacement address. So, and in case of format 3, how do you find out the target address? In the sense, because the target address can be found by means of, these are the two ways we do find out, as operand address minus the PC value, or in case of base relative, we do find out as operand address minus the base value or base address. So when the you observe carefully, when the relocation occurs and the starting address of the program will vary, there will be a changes in the operand address and there will be a relative change in the PC and the base. So when there is a relative change in the PC and the base, so when there is a changes happen in the address field, so there will be relative changes which will happen in these. So the target address will never vary. It is as same as when the starting address is changed from 0 to when the starting address is 0 and the operand address is 100 and the PC is 103. I assume that the operand address is, let's assume operand address is 1000 and the PC is 3. Starting address is 0, operand address is 1000 and PC is 3. When the starting address is changed from 0 to the 2000, then this operand address will become 3000 and this will become 2003. So when you subtract, the resultant value will be same. So based on that perspective, the target address will never vary when the relocation will occur. So when the target address will never vary, so this field in the object code of the format 3 instructions will not affect. So you conclude that even the format 3 instructions will also not be affected because of your relocation. Finally, format 4 instruction. Under the format 4 instruction, how do you find out this target address? In the sense, you do find out this target address just by means of your operand address. Your operand address itself will be considered as target address. There is no means of relative address. This is the absolute address you can consider. So as you are finding out the target address by means of directly operand address, so when the starting address varies, there will be a variation which happen in the operand address also. When there is operand address changes, so definitely there is a changes in the target address. When there is a changes in the address field here, object code will vary. So I conclude that in the SICXC instruction, other than assembler directive instruction, because in case of assembly directive instructions, you will nowhere will be using the address field. So other than assembly directive instruction, all other instructions can belongs to any of these formats, either format 1, 2, 3 or 4. Among 1, 2, 3, 4, format 1 and 2 will never make use of address field, so they will not be affected because of relocation. In format 3, you do make use of address, but that is the relative address. So there is a relative changes in the operand address and the PCR base, so which will never affect. Only a format 4 instruction, as you will be considering the target address as directly as the operand address, so there is an effect to the format 4 instruction. So when the relocation occurs, there is a major effect to the format 4 instruction object codes. So that is, let us take up an example. Here is an example. So if you take up this STL return address, which has the opcodes followed by the very important Linux BP, which will, there is no modification. The finally the operand address, here it is a 02D, which I have it as a the relative address. So what is the operand here? It is the return address. What is the address of return address? It is the 0030, when the starting address it was 0. The address of this return address, it was 0030 when the starting address was zeros. And what about the PC for this? PC it is the 3. PC is the 3. So when you subtract this 30 minus 3, you got as 2D when the starting address is 0. When the starting address is modified or changed, when the starting address is changed to, let us assume, when the starting address is changed to 1000, when the starting address is changed to 1000, so this 0030 will vary as 1030, which is 1030, and this 3 will vary as 1003. So again, as usual, if you find out the relative address for this, then it is the operand address is 1030 minus the PC value is 1003, and when you subtract, obviously you will get back as 02D itself. So like this, in the format 4 instruction, as you will find out the target address by means of operand address minus PC value. So when the starting address varies, there will be a relative variations in the PC and also the operand address. So when you subtract it, the resultant target address will be same. That is why I mean to say there is no modification will occur in the format 3 instruction. Whereas modification do occurs for the format 4 instruction. Here is an example, which is plus JSub read record. In this plus JSub read record, the last 5 bytes, because if you observe in the format 4 instruction, the address field itself is 20 bits, which is 5 off bytes. So last 5 off bytes, these are the last 5 off bytes which are belongs to the address field, which is 01036. Why? Because here is the operand, it is a read record. The address of the read record, it is 1036. The address of that read record, it is 1036. As the address of this read record is 1036, so we generated the object code for this plus JSub read record as this is what the fields belongs to, the opcode and NX BPE, and followed by this is the address, and we are going to consider the target address, which is same as the operand address. And where is this read record? Here is the read record. The address of that is 1036. So that itself we are going to consider directly as the, which is 1036. For that even we will be adding 0 more. So to make it as 20 bits of address. What this is when the object code of this plus JSub read record you got as 4B101036, when the address of this read record is 1036. That too when the starting address it was 0. Per suppose when this is relocated because of the memory constraint, if it is relocated to 1000, assume if it is relocated to 1000, then this will be this, instead of starting address is zeros, it will become 1000. When the starting address becomes zeros, then the address of this read record will become 2036, which is 2036. When the address of this becomes 2036, the object code will never be remained same. Here instead of 4B101036, it will become as 4B102036, wherein the address of the read record is modified. Again, as usual, when the starting address is changed from 0 to the 5000, then the address of this read record will be 6036. Then the address of this read record will be 6036. In such case, the object code of this instruction will vary as 4B106036. That is what I mean to say. In format 4 instruction, as you will take up the operand address directly as a target address. So whenever the starting address varies, address of such operands will vary. When the operand's address will vary, the object code will also varies. So there is a necessity of writing the modification record for this format 4 instructions only. There is no need of writing for format 1, 2 and the 3 instructions. So there is a need of dealing the relocation of the format 4 instructions only. So that is what we see now. So here there are all this is the 2 more subroutines whatever we studied in the previous concepts. So again you may get the question, here it is the one more format 4 instructions, but doesn't it requires the modification record, or will affect because of relocation access? No, it will not affect, because you can observe in case of plus LDT 4 #4096, Here we are not going to use any operand address, because the 4096 itself will be acting as 1000 in the hexadecimal as the address here, a target address. So it is not the operand address, it is the target address, which is the operand value. So even though this is format 4 instruction, which will never get affected because of your relocation. So in this example, these are the three instructions, which is place JSF read record, place JSF write record, and place JSF write record, because they are the operands and they has the addresses. So 1036 and here it is 105D for the write record. So when the starting address varies, the address of these will also vary. When the address of these will vary, the object codes in these instructions will be varied. That is what we say. In case relocation directly affects the format 4 instructions, because you take up the operand address directly as the target address. Now let us this solution part. However, we already said here for the SICXC how to handle the relocation, in the sense that is by having the modification record. So now let us have the modification record in the object program. So before you know that, I hope you know this modification record, how to write the modification record. This is the format of the modification record. For M followed by the starting address. It is not the starting address of the instruction. It is not the starting address of the instruction, or it is not the starting address of the program. It is the starting address of the object code from where the modification is required. Then length of the object code. Then it is length of the object code, how many of bytes to be modified, which is length of the object code to be modified. And then you have modification flag. It is either it is whether you are going to add up the address or subtract the address with the specific address. And finally we have the external symbol, how much to be added or how much to be subtracted. So we are going to take up this in the same way. Now here, when you take up this example, and already I said with respect to this example, as there are 3 instructions which requires the relocation to be taken care, so you need the 3 modification record. Rest of the object program, it is as usual. However, we had studied in the previous classes, as you have header record, text records, and the end record as well. Now let us see about this modification record. So first it is M followed by, now let me write for this instruction, which is plus JSF read record. So as usual, for when you write the modification record for this instruction, so assume this is what this is the object code generated for this plus JSF read record, wherein the address of this instruction is 6. Address of this instruction is 6, but that address, it is something like this is the 6th byte, this is the 7th byte, this is the 8th byte, and this is the 9th byte. So the 4 bytes of this format 4 instruction are, this is the address of this, it is these two 4B, it is 6, address of 10 is 7, address of this 10 is 8, and address of this 36 is 9. Again observe carefully, when the address of the read record will varies. Now the address of read record is 1036. When the address of read record varies as 2036, remember that will be varied only with respect to this address field only, not everything, because I already said the last 20 bits it is the address field. So based on that last 20 bits only that address will vary, not everything. In that perspective, modification belongs to this 4B1, which are belongs to the opcode and NXBPE, which will never vary. So this is the object code belongs to the 6th byte, which doesn't need the modification, wherein in this 10 the address will start from this 01036. This 01036 belongs to the address field. So as this 01036 belongs to the address field, and it is starting from the 7th byte, it is starting from the 7th byte. This is the byte 7. So as it is starting from the 7th byte, so modification is required from the 7th byte onwards, not from the 6th byte. It is required from the 7th byte onwards. So that is the reason here, if you observe, it is M followed by 7. And why this 5? In the sense, it is totally 20 bits of address to be modified. 20 bits is nothing as 5 off bytes. 20 bits is nothing as 5 off bytes. Then again the modification flag, why it is plus and copy, in the sense, see now the address of that read record is 1036, and when the starting address varies, it may be incremented. it may be incremented. For that it is plus, it may be added with, so only it is plus. And what value will vary? So you observe here carefully, when the starting address was 0 and the address of this read record it was 1036. When the starting address varies from 0 to the 1000, when the starting address varies from 0 to the 1000, so when it is changed to 1000, so what will happen? This will become 2036. Based on what you are getting? Based on this 1036 plus what is the changed starting address, which is 1000. So 1000 plus 1036 you will get as 2036. Again, as usual, if the starting address is changed from 0 to the 5000, assume this is changed to the 5000, you need to add that 5000 itself to this address. You will get the current value, which is 5000 plus 1036, you will get as 6036. So that is the reason a flag bit is plus, and what used to be added, it is the starting address, which is copy. Here you can observe it is the starting address, which is the copy address, which is to be added. So that is the modification record for this plus JSub read record. Let's see for this plus JSub write record as well. Again, if you observe, this 4B1 belongs to the object code and NXBP, whereas address field is 0105D. 0105D. So the modifications is required. What is the address of this instruction? It is the 13. The address for this instruction is 13, and the modification doesn't require for the 13th byte, because this is belongs to the opcode and NI. And whereas the modification is required from the 14th byte onwards, because this has 10105D, wherein even though address started from this 0105D, so the modification required from the 14th byte onwards. And again, how many off bytes? It is the 5 off bytes. And what is to be done? It is the plus value with what? With the starting address. That is what we write here. From the 14th byte onwards, you are supposed to modify. And how many off bytes? It is the 5 off bytes. And what is to be done? It is plus or minus. It is the plus added with the new value. So like that, you will have to generate the modification records for each format for instruction, which is to be wherein the object code may vary because of the relocation. So that is what how to handle the relocation in SIC in the sense by having the modification record. For that itself, we saw which are all the kind of the instruction which will vary. It is only the format for instruction, and how to deal with that, it is by having the modification records in your object program. That is how you deal with the relocation, or how does your relocation loader will come to know which are all the object codes to be relocated or modified. Now let us see the relocation with respect to the SIC. So dealing with relocation with respect to SIC. So if you want to deal with relocation with respect to SIC, again as usual, first let us assume this is the example of SIC program. And in case of SIC program, if you remembered, how did you generate the object code for this STL return address, in the sense, because the format of in case of SIC instruction we had as opcode of 8 bits followed by 1 bit of X bit and followed by 15 bits of address, which is the operand address itself will be considered. Now, how did we generate the object code for this STL return address? You assume this is the opcode, which is 14. And what is the return address of this return address? It is the 0033. That itself we used. Again, what about this plus JSub read record? 48 is the opcode of JSub, and read record. What is the address of read record? It is the 1039. That itself we used. Again, LDLN 00 is the opcode, whereas length, what is the address of length? Like 0036. Like this, for every instruction we made use of the address field. Especially we made use of address field as directly the operand addresses itself. Now, suppose if the relocation occurs, when the relocation occurs, this 0 may change to the 5000. When the 0 changes to the 5000, the address of this return address will become 5033. So in such case, this object code will never be remained as, it will not be remained as 140033. It will become as 445033. It will become as 445033, wherein this will become 6039. In such case, this object code will become 486039. What about this LDL length address will be 5036, so it will become 0050 5036. Likewise, when there is a modification which will occur, all the set of instructions will vary wherever you are using the operand address, because when the starting address will vary, the operand addresses will vary, and wherever you are using those operand addresses for generating the object code, so for such object codes will vary. So that is how. So does the relocation affect the SIC program? In the sense, it is yes. But which are all the instructions which will be affected because of the relocation? In the sense, whichever the instruction which is making use of the operand address to generate the object code, the instruction wherever you are using the operand address to generate the object code, all those instructions or all those object code will be affected because of relocation, and which has to be modified or which has to be updated at the time of loading. That is what you said as affecting the relocation with respect to SIC. Now let us see the result, I would say solution part. So where we will be dealing with the relocation bit. What is this relocation bit? In the sense, just setting that relocation bit either with the 1 or 0. See, understand, as there are so many instructions, and there is a necessity of modification of the object codes of so many instructions, you can't keep writing the modification record for every instruction or every object code. So that is the reason where we take up only the modification bit. You assume here this modification bit means to say that there is a necessity of object code to be modified. If the object code is if there is no need of modification, then set that modification bit as 0. So if there is a necessity of relocation, then set the relocation bit as 1. If there is no necessity of relocation, then set the relocation bit as 0. Here is an example. See, till here, see, it is LDL return address. Address of return address is 0033. If it varies, so this object code will vary. So till that I set the relocation bit as 1. Wherein for this R7, I set the relocation bit as 0. The reason that there is no operand at all here. When there is no operand, so we did not make use of operand address here, we simply set as zeros. When there is no operand and we simply set as the operand address as zeros, so there is no need of you to bother about the relocation, so it will be retained same, so it is 0. And these are all the assembly derivative instructions. These are the assembly derivative instructions which are nowhere dependent on the address to generate the object code, because for this EOF, it is the object code, it is E45, O4F, F46. We did not make use of any address for this. Again, for this 3 itself is the object code. For 0 itself will be the object code. So for assembly derivative instructions, we did not make use of any of the address. We did not make use of any address for generating the object code, so that we set the relocation bit as 0 for this. Again, moving together. So moving to the next, again here again as usual, LDX 0. The address of this 0, it was 0030. So we set it as relocation bit as 1 because it may vary. Wherein again as usual for RSA, byte and word, which is assembly derivative instructions, where it is again as usual relocation bit we set as 1. So like this, you just set the relocation bit either 1 or 0 based on the possibility of modification is required or not. So where to deal with this? In the sense, these we are going to write in the object program. So you understand clearly, this is what the field. So in the text record, however we had, which is T followed by the starting address of the text record followed by the length of the text record. Right after the length of the text record and before the beginning of object codes, I repeat, after the length field and before the object code field, here we are going to have a 12 bits, which is 3 off byte length. These bits will give you the relocation bits. These are the one which will give you the relocation bits. So what I mean to say in the sense, see, based on my relocation bits, I have just identified here. See, for this relocation bit is 1, for this second relocation bit is 1, for this second relocation bit is 1. Like this for all these. So till 40 the relocation bit was 1. So till here for all the object codes, the relocation bit was set as 1s. So like this, it was all set as ones. So again you group every 4 bits together. See, relocation bit of this is one, this is one, for this again, for this one. So 4 ones, it is what, nothing else, f. See, this 4 ones, which is nothing else, f. Again next 4, again next 4, you got again ones, so it is f. Again last 2, for this it is 1 1. So as these are double 1, the rest we are going to have it as double 0. So it will become as double 1 double 0, which is C. So this modification, or you can say that relocation flag, a relocation value, a relocation bits, it is FFC, which is FFC, because first 4 bits need to be modified, so you got F. Again next 4 object codes need to be modified, you got F. Again last 2 object codes to be modified, so you got C, because after it is double 1 double 0, it is we are going to add double 1, 2 more zeros for this double 1. Again moving to the next text record, again as usual, again for this, if you take up from here if you take up, you got as, if you observe from here, we got as 111 4 zeros. So you got as 111 4 zeros. Again as usual, because it means to say that these 3 need to be modified, so these 2 need to be relocated, so set 1 1 to 1 1 1. Again this doesn't require modification, so 0. Again this doesn't require modification, 0 0 0, like this. So this 4 bits, if you group together, it will become 1110, which is E. Again you have only 3 zeros, rest also you are going to make it as zeros, so only you got as E00, which is the modification value. The modification value generated based on the modification bits of each and every object code, based on whether it is 1 or zeros. So like that we are going to set for further object codes also. We are going to take up this modification bits. You set modification bit as 1 if there is a necessity of modification, set 0 if there is no need of modification, and those bits, those modification bits need to be grouped 4 4 each together, and those itself, based on that itself, you find out the modification value. And remember, these modification value bits you are going to insert after the length and before the actual object codes in the text record. In case of SIC you are supposed to have separate record, which you call as modification record, in case in your object program, whereas for in case of SIC machine you don't need to have separate modification record. Those modification bits or relocation bits can be inserted in the same text record, but way to insert it is after the length field and before the object code field. You will be having these modification bits. I repeat again, if there is a necessity of modification, set with 1. If there is no necessity of modification, then set with 0. Based on that you group every 4 bits together and generate the modification values, and these are the modification values which we generated based on these bits, and these bits are generated based on these object codes, whether there is a necessity of modification or not. That is how you deal with the SIC program, or you can say that applying the relocation loading process with respect to SIC. So I hope you understand. So in case of SIC, only format 4 instructions will be relocated, or there is no necessity of relocation for format 4 instructions. And how to deal with it, write the modification record for such instructions. In SIC, all the instructions whichever make use of the operand address to generate the object code will be affected. So set with the modification bit, or you call as relocation bit, with 1 or zeros. Where there is a necessity of modification, set with 1. If there is no necessity of modification, set with 0. So those itself will be inserting in the text record of our object program, which is after length field and before the object codes. So by grouping every 4 bits together, so this is what the relocation flag bits. So I hope you understand. Till now we saw the procedure. Now let's see the algorithm. How does the relocation loader works for SIC and also SIC. So first let us take up a SIC. So if you see this, first you should get the starting address from where? From the operating system, and that starting address I am calling here as a program address. So this program address is the starting address from where the loading has to begin in the main memory. So as soon as you get the starting address, then you read the record from the object program. if the until you reach to the end record, so from the text record you keep loading. So if there is a text record, you keep loading the object code into the main memory. So but where is supposed to load, in the sense it is the location which is specified with the program address and the specified address. It is the plus. See what is this and what is happening here, in the sense. But suppose again let me take up this example itself. But suppose if there's based on this program address, this is the specified based on this example program, this is the specified address as 0368 something like this. But suppose this program address which is given by the operating system, which is 1000, then it will be as such that. And where is supposed to load the object code of this JEQ end fill? Where is supposed to load? It is the program address which is given. What was this program address? It was given, I said it is the 1000 plus the specified address of this. What is the specified address of this? It is the 10. So 1010. So the object code of this instruction, which is 332007, it's supposed to be loaded at 1010. How did you get it? You got it from the starting address which you got from the operating system, which is 1000, which is the program address in my means, plus the specified address, it is the 10. Again let us take up this example as plus JSF write record. Where does this has to be stored? Again as usual, program address plus specified address. What is the program address? It is the 1000 plus the specified address is 26. So it has to be loaded at the 1026. That is what here it is says, that you need to, from the text record, from this text record you keep pushing these object codes into the main memory where it has to be loaded from. It is the program address plus the specified address, so you need to keep loading into it. Then for the object codes which are specified with respect to the modification record, those object codes need to be modified. And what modification is to be done? So understand what modification is to be done. Per suppose again, if I take up this example itself, this is for this we have the modification record. What we supposed to do? We need not to modify anything related to this opcode and NAX BPE. We supposed to modify only with respect to the address. So earlier it was 1036. So now if it is changed, if the starting address is changed from 0 to 1000, then this has to become as 2016. So how did you do that, or what did you do? You added the program address with this specified address. What is the specified address? It is 1036, that you added with the current program address. So you got us 2036. That is what we do in the algorithm. Whatever it is already available specified address, for that you are going to add the program address. You are going to add the program address, for which you will be doing this only for the modification record. So that's what, if the record type is M, then you need to add that program address value in the object code wherever you have that modification record. So this is what the simple object or a simple algorithm for the relocation loader process with respect to SIC. Now let us see for the SIC. So in case of SIC also, I hope you remembered what we did. First we identified with the whatever the object codes need the modification. For that only we use it as 1, which doesn't require, use it as zeros. So per suppose this is the object program given by the assembler. How does your loader will treat this and will modify object codes and write it to the main memory? That's what let's see now. So again as usual, you get the starting address from the operating system, then you're going to, until you reach to the end record. In the text record itself, if you observe in the text record itself, the assembler already given this mask, I can say bit mask field, because the set of bits which are masked together in the form of a bit mask here. So if it is available, you have observed this in the text record. If there is a bit mask field, for that bit mask field, then you have to elaborate such a way that if the bit value is 1, then only there is a necessity of modification. If the bit value is 0, then that doesn't require modification. That can be directly, you can directly move that to the main memory. If it is bit 1, then there is no necessity of modification. And also, what is the modification? Just you will be adding the current program address with the specified address. Again, let me take up this example here itself. With respect to STL return address and the starting address was 0, the object code you got is this 140033 because the address of this return address is 0033. So your assembler has considered this and it also set the 1 for this, which is the bit, relocation bit. Now per suppose if this address is changed to the 5000, then the program address, the starting address which is the program address will be 5000, then even this will become 5033. So what is supposed to do, that 5000 has to be added with this specified address in the object code. That is what we are supposed to do. If the bit is 1, the modification bit is 1 which is assigned by the assembler, if the modification bit is 1, then the loader has to add the program address with the specified address. If the modification bit is 0, then the loader need not to add it directly, it can load that. So in such kind of these kind of instructions which doesn't require the modification, these instructions and these instructions which doesn't require modification, those can be directly loaded to the main memory. That's what a simple algorithm for SIC relocation loader option. Thank you.